take a look at my whiteboard. This is the equation we have so far, right?
Yes.
All right. Now the next thing I'm going to do
I see.
is square the 5. What's 5 squared?
25.
Now there is no m equals 25. The equal sign is on the left-hand side over here.
I see.
All right. That's why I said we can't really solve for m, because we have 2 unknowns here still. So we have to be careful with our algebra. So the next calculation step is just to do the 1/2 times 25. So that's, what would that give us?
Let's see. $12.5.
So our final formula for I is 12.5 times m, right?
Right.
Okay, not 50. So you just have to take your time and write down each of those calculation and algebra steps carefully. All right, now what am I going to do with this I? Well, now I can go back and plug that I up into our equation up here, right? So I'll go back and plug that in. Okay. Okay. So let me make a comment here. A lot of people kind of would not even bother calculating I here, because a lot of people kind of give up too soon. A lot of people say, "Gee, it's pointless to worry about I because I don't know what the mass is." But notice that even though we don't know what the mass is, it's still useful to get an expression for I. Even though we haven't got a number for I, we still got an algebraic expression, 12.5 times m. So it's still very useful to have gotten that algebraic expression. Okay. So we went back and plugged that in over here. All right, so again, to review, how do you find the moment of inertia? Well, for a point mass, you use mr squared. But for an extended object, you use your table in the book. How do you know, then, when it's an extended object and when it's a point mass? Remember that if the problem tells you the shape of the object, well, then you need to use the table in the book. If the problem tells you the shape of the object, then it's an extended object and you have to use the table in the book. Well, this problem specifically said that we had a solid cylinder. So that was the big clue that we had to use the table in the book. If the problem doesn't mention the shape of the object, then they probably want you to treat it like a point mass. If the problem doesn't mention the shape of the object, you should treat it like a point mass. Okay, so that's an important idea to have in your notes. You can't just say that I is always mr squared. Notice that in this case it was 1/2 mr squared, so that mr squared formula would have led us astray. Okay?
Okay.
Okay. All right, now looking at our equation, there's something we can do now to simplify this equation algebraically that you were already kind of anticipating. Now we can cancel the masses. I think you were kind of thinking the masses might cancel, and now we can see that they do. Would you agree with that the masses will cancel?
Yes.
Yeah, but the only reason we can do that is because now there's a mass term in every single term. You can only cancel a variable if it appears in every single term. So we could not cancel the mass until we got that mass to appear in this last term over here by plugging in for I. So this was a very important problem-solving step. And again, remember, that shows us that even though we didn't know what the mass was, it was still very useful to get an algebraic expression for I, because that allowed us to get an m in this term, and then we can cancel out the masses. All right? Okay. So we've canceled out those masses. And now there's only one more unknown that we are having trouble dealing with here, right? Now we still have that omega unknown. However, there is a way to get rid of omega and replace it with v, or to get rid of v and replace it with omega. What could we do to get rid of one of those variables?
Our new special equation, v equals r times omega.
Okay, good. That's good that you remembered that. So yeah, we can use v equals r times omega. Now, you could either substitute for v or substitute for omega. In a way, it makes sense to substitute for omega because the question's asking us for v. That would make the algebra difficult because omega is v over r. Does that make sense? Omega is v over r? But if we plugged in there, we'd have a fraction. So why don't we actually plug in for v? Let's plug in r omega for v. Well, first of all, we actually know what r is, right? What's our r?
10 meters.
Now, there's two different distances here, the 5 meters and the 10 meters. Which do you think the r stands for?
Well, I would think that the r was 10 meters.
Okay, so yeah, I should have explained that more clearly before. So this formula here tells us how quickly something is rotating, right? It has nothing really to do with how far it's moving. This is telling us how quickly something is rotating. It kind of makes sense, doesn't it, that if you're rotating more, if you have a bigger rotational velocity, you would also have a greater linear velocity. So this equation just says that the more you're rotating rotationally, the bigger your translational velocity will be. But if you think about it, then what matters for how fast you're moving is the shape of the object, not the path. So the R here stands for the radius of the object.
Really? Okay, so this is not the same R that we were trying to find from our... okay. All right, I see.
And actually, in a sense, this really is the same R we've been using previously in this chapter, because we always said R was the distance from the axis of rotation, right? In this chapter, we're using R as the distance from the axis of rotation, right?
No. I mean, not that I remember. Oh. I remembered that R was something else, but I could just be confused.
Okay. Well, remember when we were working with torques last time, when we were drawing the R vectors, we said that R went from the pivot to the point of application of the force?
Right,
yeah.
From the pivot.
Now, maybe I should have made clear, the pivot is the axis of rotation, right? The pivot and the axis of rotation are two names for the same thing. The pivot point is just the point that you're rotating around, and the axis of rotation is the line that you're rotating around. So if R is going from the pivot point, that means it's going from the axis of rotation. So anyway, then our pivot point, or our axis of rotation here, as you mentioned earlier, was the center of the cylinder. So R should be measuring our distance from the center of that cylinder. Okay.
Okay.
Well, then what would we plug in for R here?
So it would be the 5 meters.
Okay. Okay, anyway, you should just make a note that when you use this equation, R stands for distance from the pivot, or distance from the axis of rotation, which basically means the radius here.
Right. I see now.
All right, back on track. All right, so anyway, now we can start plugging in. So our new equation is 9.8 times 3.4 equals 1/2. Now, instead of V final, I'm going to plug in for V final. So what am I going to plug in for V final now?
I have no idea.
Oh. Well, so let's go back. So we said here that we're using our V equals R times omega equation, right?
Mm-hmm.
So in this case, that would be V equals 5 times omega.
Oh, okay. So you're... okay.
All right.
I guess I missed that part of it. Okay.
Did you see where we got the V equals 5 times omega?
Yes. Mm-hmm.
Okay. But so we could say that V final equals 5 times omega final, right?
Okay.
So what can I plug in for V final? 5 times omega final.
Okay.
And I can't forget to square that.
Okay.
Okay. And then we have plus 1/2 times 12.5 times omega final squared. Okay?
Okay.
All right, well now what? Now we just have a bunch of algebra, right? We only have one unknown left. Once you only have one unknown, you can just use algebra to solve your equation?
Mm-hmm.
Okay, so we should start making some calculations. So tell me, what are some calculations that we can make here that would simplify things for us?
9.8 times 3.4.
Okay, let's do that. Tell me what you get when you're ready.
Oh, I'm sorry. It's 33.32.
Good. Okay. Any other calculations we could do?
Yeah, we could do the 1/2 of 12.5.
Okay. Tell me what you get there.
6.25.
And we can't forget that it's still times omega final squared. Good. Any other calculations? Do you know how to simplify this term here?
You would just square the 5, you get 25, and then take 1/2 of that.
Good.
So
now let's write that down carefully. Because both the 5 and the omega are being squared, we can rewrite this like this. We can say that we're squaring both the 5 and the omega. All right, and then So that's very important. That would important to make it clear notes on that. Otherwise, we'd get have made an algebra mistake here. we're squaring that whole thing because remember that stands for the v final squared.
Right. Okay.
All right. So now what do we get from that calculation?
It would just be 12.5 omega final squared.
Good. 1/2 times 5 squared is 12.5. All right.